In superconductivity, today we are going to discuss the thermodynamics of superconducting transition. When you say superconducting transition, that means transition of the normal state of a material into the superconducting state and vice versa. It means it is also possible that there will be a transition of superconducting state into the normal state of the material. Actually, this transition must be reversible. I hope you have studied the phase transition, particularly the first order phase transition and the second order phase transition in your course on thermodynamics. And if you have not a concrete knowledge of first and second order phase transition, which we study in thermodynamics, then I will suggest you to go through my videos on phase transition in the playlist of thermodynamics of my channel, where you will get a detailed explanation of first and second order phase transition. Okay. In fact, thermodynamics is well applied for the reversible processes. Okay. And you have studied Meissner effect in very detail previously, and you have seen that actually Meissner effect shows that the superconducting transition is reversible. It means according to Meissner effect, when a superconductor transits from normal state to the superconducting state or the superconducting state to the normal state, then actually this is possible actually in both directions, and so we simply say that this transition is a reversible process. Just like for example, you can transform a liquid into the vapor state and a vapor into the liquid state. So if you consider that the normal state is just a liquid state, just for analogy, and the superconducting state is the vapor state. Okay, so as a liquid on heating is transformed into the vapor state, vapor phase, and when a vapor is cooled, then it is transformed into the liquid state. Okay, just like that, according to Meissner effect, a superconducting material can be transformed from normal state to the superconducting state and from the superconducting state to the normal state. So we simply say that Meissner effect predicts the superconducting transition is a reversible transition. Okay, and as it is a reversible transition, so we can use the thermodynamical idea of phase transition between the superconducting state and the normal state of the conductor or material. Okay. Actually, in our present discussion here, we are going to see the phase transition between the superconducting state and the normal state only for type 1 superconductors. Okay, and you know this type 1 superconductors you have studied earlier in very detail, that these are the superconductors which strictly follow the Meissner effect. And when you say that type 1 superconductor strictly follows Meissner effect, what does it mean? It means the magnetic induction B is equal to 0 inside the conductor. Okay. Now, when you will study, when you have studied actually the phenomenon of phase transition, then you have seen that actually phase transition always takes place at a particular pressure and temperature. Okay. So during a phase transition, pressure and temperature both remain constant. So phase transition is simply called that it is an isobaric isothermal process. When you say isobaric process, it means pressure is constant. And when you say isothermal process, that means temperature is constant. So definitely phase transition is always an isobaric isothermal process. Okay. So if your aim is here to study the phase transition between the normal state and the superconducting state of a material, definitely you have to think about the isothermal isobaric process. Actually, when we consider there is a phase transition from one phase to another or one state to another, then definitely at a particular pressure and temperature this phenomenon takes place, and the both phases of the system remains in equilibrium. Okay, so we will study the superconducting transition under this condition, that is in isothermal isobaric process, when two phases, that is the normal and superconducting phases, are in equilibrium. Okay, and you have also studied in your course on thermodynamics the different thermodynamic potentials. One of the most important thermodynamic potentials or functions is a Gibbs potential or Gibbs free energy function, and it is denoted by the symbol G. And you know, this Gibbs function or Gibbs free energy remains invariant or remains constant during an isothermal isobaric process. And since it remains constant during isothermal isobaric process and any phase transition takes place in isothermal isobaric condition, so this Gibbs potential or Gibbs free energy function is the most suitable parameter or most suitable candidate to deal with the problem of phase transition. So here also in the case of phase transition between the normal state of a material and its superconducting state, we will start to deal this problem by taking the Gibbs function or Gibbs potential under account. Okay, and we will actually, our aim is actually to know some of the thermodynamical properties, how it changes when phase transition between the normal state of the material and its superconducting state takes place. Okay, so let us start with the Gibbs potential. You know, Gibbs function is defined in this manner. This definition you will find in thermodynamics. G is equal to U plus PV minus Ts. I hope you have an idea of all the quantities used in this expression. Actually here, this U represents the internal energy, P is for pressure, V is for volume, T stands for temperature, and S for entropy. Okay, and this is the basic definition of Gibbs potential. This G is equal to U plus V. It is also written as H minus TH, where H is called enthalpy, which is actually the sum of U and PV. Okay, but here when you talk about the superconducting phase transition, then you know this transition is actually governed by the magnetic field too. So here we will transform some of the quantities in this expression, particularly when we talk about our material is inside an external magnetic field, and magnetic field is also responsible for the phase transition. Actually, you know, P, which is pressure, that is just equivalent to a tension. There is force acting on unit area, so this is just equivalent to tension. And this magnetic induction B is actually equivalent to that. And you know B is equal to mu naught times H. So if you will apply this expression of Gibbs potential in case of the superconducting phase transition, then we will replace this pressure P by mu naught times H. This mu naught times H is just analogous to P. And similarly, the magnetization M, this is analogous to minus V, negative of volume. So the expression for Gibbs potential, okay, or Gibbs free energy per unit volume will be what? This will be G equal to U minus Ts, okay. And instead of P, we will write mu naught H, and instead of V, we will write minus V. So this is minus mu naught Hm. So now you can say that this is the basic definition of this Gibbs potential or Gibbs free energy. Okay. Now to get the final result, we have to make some calculation, and that will need some mathematical steps, and that steps can be memorized by practicing. Okay. So let us first of all take the differential of this equation 2. See this equation and take its differential. This will be dg equal to du minus differential of t times s. Here there is a product of two functions. So this will be minus tds times minus s dt. Okay. And mu naught is a constant. And again, we will have to take the differential of the product of h and m. So this will be minus mu naught h dm and minus mu naught m dh. Okay. This is the change in Gibbs potential dg. Okay. Now, according to first law of thermodynamics, you know, this change in internal energy du is given by del q minus p dv. Actually, p dv stands for the work done in the thermodynamic process, and del q is the heat energy. But you know, from second law of thermodynamics, del q is equal to T ds. This is actually the second law of thermodynamics. Okay. So instead of del q, now we will write T ds. And just you have seen that instead of P, we can write mu naught H. Okay. And instead of dV, we will have to write minus dm. Okay, because m is analogous to minus b, so dv will be analogous to minus dm. So du is given as tds plus mu naught h times dm. Okay. Now we will substitute this value of du which we have obtained in this equation 4 in this equation 3. Instead of the first term du in RHS of equation 3. So let us substitute this. So making this substitution, our equation 3 will now become like this. This is dg equal to tds plus mu naught h dm minus tds minus sdt minus mu naught h dm minus mu naught mdh. Now you can see this tds and this minus tds will cancel out, minus mu naught h dm and plus mu naught h dm and minus mu naught h dm will cancel out. And so we finally get that dg is equal to minus s dt minus mu naught times m dh. Okay. But as we are considering the isothermal isobaric process, so in isothermal process, you know, temperature T remains constant, and so dt is equal to 0. So let us put dt equal to 0 in this equation 5, and then you will get that this change in Gibbs energy dg is simply equal to minus mu naught times m dh. Okay. So in this way we have obtained the change in Gibbs potential. Okay. Now, if you if you talk about the normal state of our material, actually it is found that it is experimental fact, you can say, that the normal state of most of the superconductors is paramagnetic. Normal state, not the superconducting state, is diamagnetic. But the normal state of most of the superconductors is paramagnetic, and so its magnetization M is very small compared with the superconducting state. Actually, magnetization in case of superconducting state is larger in comparison to the magnetization in case of normal state, because that are actually paramagnetic behavior. So in this equation 6, this M is will be can be neglected or can be taken as 0 when we talk about the normal state of the material. Okay. So in case of normal state, we can say that this dg will be equal to 0, because for normal state we will take m equal to almost 0, and so dg will be 0. Okay. So you can say that the Gibbs function Gn, here n subscript stands for normal state. So when you say Gn, this is Gibbs potential for normal state. Okay. So Gibbs potential or function Gn in the normal state is not changed. Its change is 0, you can see here, by the application of the magnetic field. And as it does not change with magnetic field, so its value of G for normal state of the material will be same at any magnetic field. So let us say this Gn of Th, this is Gibbs potential for normal state of the material at temperature T and magnetic field H. Okay. And that will be equal to Gn of T0. It means this is Gibbs potential at temperature T and when there is no magnetic field, because dg should be 0, so this should be same at all magnetic fields. So here I have written Gn at when the magnetic field is H, and again in RHS there is Gn, which is the value of Gibbs potential for normal state of the matter at 0 field. Okay, and both will be same. So Gn Th is equal to Gn T0. Okay. Now, as you know, in case of Meissner effect, in the superconducting state there is no magnetic field inside the material, so B is equal to 0, and this superconductor in according to Meissner effect just exactly behaves like a perfect diamagnet. And if it behaves like a diamagnet, its magnetic susceptibility will be equal to 1. So chi, which represents the magnetic susceptibility, that is defined by m over h. This is ratio of m and h, and that is equal to -1. You have already studied this. So in this case, m will be equal to -h, and so dm will be equal to -dh. Okay. So making the use of this result in this equation 6, you can write this dg will be equal to what? Minus mu naught m dh, but instead of dh now we will write minus dm, so that will be plus mu naught m dm. So you can see dg will be then equal to mu naught h times dh. Okay. Now to find the total change in this Gibbs potential, let us integrate this equation. And we have taken the two values of Gibbs potential. One is when field is 0, and this is the lower limit. This is for the superconducting state. Mark it. Here I have written GS, and GS stands for what? GS stands for Gibbs function for superconducting state. Okay, superconducting state. Okay, and Gn stands for Gibbs function for normal conducting state. So dg integral of dg between the limit gs at t equal to t and h equal to 0, and the upper limit is gs at temperature T and magnetic field Sc, where Sc is the critical magnetic field. And you have learned about this critical magnetic field in the previous lecture. And this will be equal to mu naught integral of h dh between the limits 0 and Sc. Okay, 0 and Sc. Because you have taken the initial value of magnetic field 0, so the lower limit in RHS is 0. And upper limit of H is Sc. Okay. So this result will be simply Gs at T, Sc and minus Gs of T, 0. Okay. And this will be equal to half mu naught Hc square. Okay. So Gs at temperature T and magnetic field Sc is equal to Gs at temperature T and magnetic field 0 plus half mu naught Hc square. Okay. So this equation actually relates the Gibbs potential for the superconducting state of the material when no magnetic field is applied and when magnetic field is equal to the critical magnetic field Sc. Okay. And it is clear from this result that at the critical field, the Gibbs free energy of the normal and superconducting state must be same. Gibbs free energy must be same for the normal state and the superconducting state at critical temperature, critical field. Why? Because at critical field, phase transition takes place. And at the phase transition is just the point when our material changes its state. Okay. So at that condition, the two states of the system are in equilibrium. And since they are in equilibrium, so any property of the system in both states during that period must be equal to same. So at critical field, since phase transition takes place, so the value of free energy for the normal state and for the superconducting state must be same. Okay. And therefore, I have written here that Gn, this is the Gibbs function for normal state when temperature is T and field is Sc, and that will be equal to Gibbs function for superconducting state Gs at temperature T and field Sc, because Sc is the critical field where phase transition takes place. Okay. Now we will combine this equation 10 and this equation 9. You can see instead of this Gs at temperature T and field Sc, you can write Gn at T and Sc. So in this equation 9 in LHS, this Gs is replaced by Gn. So I have written here, you can see Gn at temperature T and field Hc is equal to Gs at temperature T and field 0, that is equal to half plus half mu naught Sc square. Okay. Now we will also combine this equation 11 with the equation number 7. You can see here Gn at temperature T and field 0 is equal to Gn at temperature T and field H. So in this equation 11, this Gn at field Hc can be replaced by Gn at temperature T and field 0. So finally we get that Gn at temperature T field 0 is equal to Gs at temperature T and field 0 plus half mu naught Sc square. Actually this is the basic equation from which we can discuss the phase transition between the normal state of a material and its superconducting state. Actually this equation is also known as Gorter's equation, and this is the basic or fundamental equation of superconducting phase transition. Okay. Now actually with the help of this equation we will learn about the change in entropy and change in a specific heat when the superconducting phase transition takes place. This is our aim. But before that, you know, when H is greater than Hc, okay, then Gs is greater than Gn, where Gs is the Gibbs potential for superconducting state and Gn is Gibbs potential for normal state. Okay, so it interprets that the magnetic field H greater than Sc, for the magnetic field H greater than Sc, the normal state is more stable. Okay, or in other words you can say the material cannot be in superconducting state. Okay, so it is also expected, because you have already studied earlier that a superconducting state is destroyed, or a material lost its superconductivity when the strength of the field exceeds the critical field. Okay, so this is the expected result. Okay. Now we will talk about the entropy change during this phase transition. And so let us see first of all how entropy will be defined. You know, in terms of G, entropy of the system is defined as minus dG by dt at constant P and H. This is the basic definition. Okay. Instead of this ordinary differentiation, we can also write the partial derivative. Okay. Now, we have to know about the change in entropy between the normal state and the superconducting state. And we have the basic equation here, that is this equation Gs, yes, this equation 12. Okay, and from this equation you can find the entropy of the system in the normal state and in the superconducting state. And for that, let us just differentiate this equation 12 with respect to temperature T. Okay, so this will be dGn by dt equal to dGs by dt, okay, plus half mu naught, and there is Hc square. So first of all, Sc square will be differentiated with respect to Sc, that is 2Sc, and then Hc is differentiated with respect to T, which is dsc by dt. Now this 2 and this 2 will cancel out. But according to this definition, you can see, since S is equal to minus dg by dt, so dgn by dt will be simply equal to minus Sn. Here n subscript again refers the normal state. So this Sn is the entropy of the material in normal state. Okay. And this dgs by dt, this is minus Ss. Ss is the entropy of the material in superconducting state. Okay. And plus mu naught Sc times dsc by dt. Now you can change the sides of the terms, and you can see Sn minus Ss will be equal to minus mu naught Sc times dsc by dt. Okay. So this is the expression for the change in entropy of our system when its state is changed from normal state to the superconducting state, or superconducting state to the normal state. That is when the superconducting phase transition takes place. Now let us see. You know that when temperature T is equal to Tc, then Hc is equal to 0. When T equal to Tc, Hc is 0. You have learned earlier in our previous lecture that this Hc is equal to Sc0 times 1 minus T square over Tc square. You have learned earlier. And from here you can see when T is equal to Tc, then Hc will be equal to 0. We know it. And if Sc is 0, the RHS of this equation 13 will vanish, and therefore you can say that Sn minus Ss is equal to 0, and that is Sn is equal to Ss. It means the entropy of the material in normal state and in superconducting state are equal. Okay, these are equal. Sn is equal to Ss. Okay, but Sn will be equal to Ss only when you are talking about the temperature which is equal to the critical temperature. But why Sn is equal to Ss? What is the physics behind it? You can learn it. You know, Tc is the transition temperature. It is the critical temperature at which phase transition takes place. And when the phase transition will take place, the both states of the system will be in equilibrium. And so definitely the entropy will have the same value. So this in this condition you can say that this entropy maintains the continuity. Okay. So I have written here, you can see, thus at critical temperature the entropies of the two phases are equal. Okay. But when T is less than Tc, T is less than Tc, then Hc will be greater than 0. It is also evident from this formula. You can see when you will take T less than Tc, then we will have to subtract something from 1, and we will get a number which is less than 1. So in that condition, Hc will be less than Hc0. Okay, and but Hc will be less than Hc0, but that will be positive. Positive why? Because we when T is less than Tc, we will have to subtract a number smaller than 1 from 1, and so a positive number we will get. So you can say that in general, when T is less than Tc, that is temperature is smaller to the critical temperature, then this critical field is positive, that is this is in fact greater than 0. Okay, and dHc by dt, this will be negative, and you can find it from here. dHc by dt, this is negative. How you can say? Hc is equal to Hc0, okay, a 1 minus T square by Tc square, okay. And now differentiate it, dHc by dt. See here, this Sc0 is constant, okay, and 1 is constant, so this derivative will be 0, and this is minus 2t by Tc square. So what you are seeing here, that this dHc by dt is equal to what? This is minus 2Hc0 t divided by Tc square. So you can see that this dHc by dt is negative, less than 0. And if it is negative, then this minus sign in RHS will become plus. And if it is plus, it means Sn minus Ss is greater than 0. And so you have seen, I have written Sn minus Ss is greater than 0, that is positive. It means Sn is greater than Ss. It means the entropy of our system in normal state is greater than its entropy in superconducting state. And you know, entropy is the measure of disorderness. If a system is most disordered, it will have high entropy. But if entropy is, let us say, 0, it means the system is perfectly ordered, not disordered. So here the entropy in superconducting state is smaller. It means in superconducting state the material is most ordered. Or you can say that the superconducting electrons are more ordered with respect to the normal conducting electrons. In other words, you can also say that the superconducting state is actually the more ordered state with respect to the normal state. Okay. So I have mentioned here, you can see, thus the entropy in superconducting state is lower, which implies that the superconducting electrons are more ordered. Actually here you can see in this figure, I have shown a graphical plot of entropy S in against of temperature. And you can see this straight line curve represents the entropy of the system in normal state, okay, and this SS, that is this lower curve, represents the variation of entropy with temperature for the superconducting state. And you can see at T equal to 0, T equal to 0K, both Sn is equal to Ss, and those are equal to 0. Actually, this is third law of thermodynamics. At 0 Kelvin temperature, entropy vanishes. So the entropy of the superconductor and superconducting state and the normal state both are 0 at 0 Kelvin temperature. But when temperature is raised, Sn remains greater than Ss. But you can see at this particular temperature Tc, when T is equal to Tc, then again you can see that this Sn is equal to Ss, which we have seen here. Sn is equal to Ss when T is equal to Tc. So this graph actually represents the variation of entropy of the superconducting state Ss and the entropy of the normal state Sn in against of temperature. Okay? And I think you have clearly now understand how this entropy changes during this superconducting transition, when our material passes from the normal state to the superconducting state or from superconducting state to the normal state. How entropy will change, that depends on temperature. Okay, at critical temperature you can see that the entropy of both states of the system is equal, but at a temperature lower than the critical temperature, when there is material will be in both phases, normal phase and the superconducting phase. Actually, in that condition, the superconducting phase has a smaller entropy than the normal phase. Okay. Now, after knowing the concept of this entropy change during the superconducting phase transition, now we are going to see the concept of a specific heat and how this specific heat will change during this superconducting phase transition we will learn about. Now again, first of all we will define the specific heat. A specific heat, you know, is denoted by the symbol C, and it is defined as T times ds by dt. T ds by dt. Actually this is a del Q by del T, and del Q in accordance with first law of thermodynamics, second law of thermodynamics, this is T ds. So this is T ds by dt. Okay. Now, as C is defined in this manner, okay, and we have obtained the result for entropy here in equation number 13. So when you will differentiate this equation 13 and you will multiply the result by T, then this equation can be expressed in terms of the specific heat. So let us differentiate equation 13 with respect to T and also multiply each term by T. You can see in the LHS of equation 13 there is Sn minus Ss, but we have to differentiate them with respect to T. So this will be dsn by dt and minus dss by dt, and then we multiply by T, you can see. And in RHS there is T, there is not Sn minus Ss. Oh, sorry. Oh, yes. T is the multiplicative factor, okay, and d dt operated on this much. T has been, by the factor T we have multiplied it, okay. Now, from this definition of a specific heat, you can see this T times dsn by dt will be simply equal to Cn, which is the specific heat of the material in normal state. And this T times dss by dt, this is Cs. This is a specific heat in superconducting state. Okay. Now see, inside this bracket there is a product of two functions. One is Hc, another is dsc by dt. So taking the product rule of differentiation under account, you can write that this is equal to minus mu naught Sct times d2sc by dt square minus mu naught t dhc by dt whole square. Okay. dhc by dt whole square. Now see, when we take t equal to tc, we have seen earlier when t is equal to tc, then from this result we know that Hc is equal to 0. So taking t equal to tc and then Hc equal to 0, what will be this result then? This will be Cn minus Cs, which has been written as delta C. This is change in specific heat, and that will be equal to minus mu naught times Tc times dsc by dt square. Okay. Actually, this result implies that if the material is cooled or warmed In absence of magnetic field, there will be a discontinuity in a specific heat in passing the transition temperature. Uh, and we also note from this equation that Cs is greater than Cn, or Cn is less than, because Cn minus Cs, it is negative here. You know that this dHc by dt, this is actually less than 0, that is negative. We have seen dHc by dt is negative, but since there is a power 2 on it, so this minus will become plus, and so this minus sign will remain here. Therefore, we simply say that this Cn is less than Cs, or Cs is greater than Cn. And you can see the graphical plot of electronic heat capacity in against of temperature here. You can see the specific electronic specific heat in superconducting state almost rises exponentially, as you can see this curve. This is almost exponential curve. Okay, and when T is equal to Tc, then abruptly this state is changed into the normal state. This is actually the normal conductor. Okay, normal. And then this electronic specific heat increases almost linearly in normal state. Okay, so there is a discontinuity in a specific heat at T equal to Tc, you can see. Okay, actually such a curve has been obtained for bismuth in experiment. Okay, so you can see I have written that at lower temperature, when superconductivity is destroyed in the magnetic field, Cs is less than Cn. It is clear that the electronic specific heat CES rises exponentially with temperature, unlike that of normal metals, for which the electronic specific heat varies linearly with temperature. Okay. So I think now you have definitely a clear-cut idea of the superconducting phase transition, which is just equivalent to a first order phase transition. Just a first order phase transition. Okay, sorry, the second order phase transition. And we have considered particularly the change in a specific heat and change in entropy in two states of the material, that is the normal state and the superconducting state. Actually, the thermodynamics of superconductors could provide a satisfactory explanation of some of the features of superconductivity, but there are many more features for which it is quite inadequate. Don't think that from this discussion or from this idea we can learn about all the properties of superconductivity. That is not possible. Okay. So I think this lecture will be very helpful to you for your examination purpose, and so definitely watch the video seriously and write your experience after learning this in the comment box. Okay, thank you very much.